This chapter is going to be hopefully also some review, but it's going to deal with a lot of classification of matter. So we talked a little bit about that in the last chapter. In this chapter, we're going to go into a little bit more detail in ways that we can classify matter. The first is going to be breaking it down into types of substances we're talking about. So the first one will be a pure substance where I have one type of atom or one type of molecule. We're talking about tiny possible particles. And the way I can break a pure substance down is it's going to either be elements or compounds. So elements meaning I just have one of those elements on the periodic table by itself, or compounds where I've combined two or more of those elements straight from the periodic table. For elements, we can have two different types. We can have an atomic element, meaning that these are elements on the periodic table that like to exist as just a single atom on its own, if we're looking at tiny little particles. One example is neon, but really most of the elements on the periodic table are going to be atomic elements. And again, their smallest possible particle is an atom. If we look at the other type, molecular elements, these are going to be ones that like to exist in pairs or like to exist in more than two of those elements combined together. We're going to focus mostly on diatomic elements where they like to exist in pairs. There are 7 diatomic elements, and oxygen is one of them. So if we're talking about oxygen or nitrogen, the halogens, all of these are going to be considered molecular elements. And because of that, its smallest possible particle will be a molecule instead of an atom. So we say oxygen molecules or nitrogen molecules. If we then look at compounds, we have also two types. We have molecular compounds, where we are combining two or more nonmetals together. So the elements on the rightmost side of the periodic table, and one example is water. Where we have hydrogen, we have oxygen. Both of those are going to be nonmetals. And its smallest possible particle will also be a molecule. If we then look at ionic compounds, now we're combining a metal and a nonmetal. All right, and its smallest possible unit is going to be called a formula unit. Since now we're talking about plus and minus charges coming together, we're no longer talking about bonding. It will be a formula unit for its smallest possible particle. So what I would do is pause here and go ahead and think of some other examples. For mixtures, we can think of them being classified in two ways. So a homogeneous mixture means that the ratio of the two or more substances I put into there are going to be the same throughout. So the ratio of those will be the same throughout. If I think about just an everyday example, if I have something like salt water, assuming I didn't have too much salt in there to make it super saturated, if everything is mixed evenly throughout, if I take a sample from, let's say it's in a cup, if I take a sample of the salt water from the top and from the bottom, the ratio of the salt to water should be exactly the same, should be uniform throughout. That's going to be a homogeneous mixture. So I challenge you to go ahead and think of many examples. There are so many examples we can think of. For a heterogeneous mixture, this is where the ratio of the substances is not going to be uniform throughout. So I can think of something, since I love food, you'll see this also as a common theme throughout the videos. Pizza. If I take one bite, so I have a slice of pepperoni pizza, I take one bite and I get a pepperoni. I take the next bite and I don't get any pepperoni. It's not evenly dispersed throughout. Another one I can think of is trail mix, right? Take a handful of trail mix and you make it one ratio with lots of peanuts and no M&Ms, and then you take another handful and you have a bunch of M&Ms. So it's not going to be evenly, or the ratio of the different substances will not be the same throughout. Okay, again, you can think of many examples. All right, so something else we want to think about and start kind of recalling from introductory chemistry, or if you've taken chemistry a long time ago, is law of conservation of mass. And basically, this is going to apply to mostly if we're performing a chemical reaction in the lab. So the total mass does not change. So we can look at this example here. Now we started in 95 with this humongous CD player and then the tiny earbuds, and now we have, well, now we use our phones for the same thing, but we have these humongous headsets. So same thing, the mass overall probably didn't change that much. If we think about this in terms of a chemical reaction, if we go ahead and weigh everything that we're about to mix together, so we're taking solutions of calcium chloride and sodium sulfate, we undergo a double displacement reaction that we'll talk about soon. And we form new products, right? So we have new products here, but if we look at the total mass, it didn't change. Now it can transform into something else, but the overall mass does not change. A few more laws, just so we kind of remember, law of definite or constant composition. So if we think about when we're combining elements together, those elements are going to be combined in fixed ratios for a specific substance. So for water, I'm always going to have 2 hydrogens, always 1 oxygen. It doesn't matter what the source is. So all these different sources, but water is water. It is a substance. Its chemical makeup is not going to change based on where the source is. So we can also look at the law of multiple proportions, and basically anytime we can combine elements in different ratios, it tells us that the mass ratio of the elements that we combine are always going to be in fixed ratios. So even though we have a different number of oxygens, when we go ahead and reduce the mass ratio of those two, it's always going to equal a whole number. So here is a sample problem for you. What I recommend doing is pausing the video and trying the problem and then taking a look at the answer and checking yourself. So go ahead and pause here. And then you can go ahead and check yourself. Here's another problem. Again, I would go ahead and pause the video. What I would think about for this problem is anytime you see a mass percent, I would go ahead and rewrite it as a fraction. It's always going to go in your get there, and it's always going to be used as a conversion factor. So when I see this, I'm going to say that the soda contains 3.0 grams of carbon dioxide over 100 grams of soda. Okay, so since it's a mass percent, it's always out of 100 grams. So go ahead and pause the video and try this problem. And you should get 10 grams. We're going to talk a little bit about theory, and I'm always fascinated by how different things come about. How did people make discoveries, especially back in the day? So I'm going to post the link to this resource so you can watch it on your own. But one of the earliest discoveries or key discoveries were made by John Dalton in 1808. So I like to think about the technology and what was available back then and thinking about how you use the scientific method at that point. But some of the key discoveries he made about the atom, or just matter in general, is first that matter is composed of atoms that can't be created or destroyed. So that's going to be the smallest unit. You can't break it down any further than that. Atoms of one element cannot be converted into atoms of another element. All atoms of a given element are alike. They have the same mass, they are identical. And then also something that we just talked about is that compounds are going to combine in whole number ratios. So if we're looking at the elements in those compounds, they're going to combine in whole number ratios. Another key discovery a little bit later was this interesting work done by J.J. Thomson. So the way this experiment was set up is that you have this evacuated tube and you have this phosphorus coated plate at the end, so it helps give this fluorescence. And if you apply a voltage across here, you have the negatively charged plate emitting these rays, and since it's negatively charged, it's going to be attracted to the anode, the positive plate, and then if you have a split, it goes straight through. So it goes straight through. And then if we apply a magnet, so a magnetic field to that, what happens is it goes ahead and it bends. All right, so since the cathode ray bends, it tells us that we have to have something else there. The particles have to be charged since it's going to be bent by the magnet. So this came about that atoms contain smaller particles. So really what we're talking about are those electrons, the things that are doing all the chemistry. This is where it all started. So again, the ray is going to bend a magnetic field, so it must consist of charged particles. So specifically, since the ray is going to bend towards the positive plate, it tells us that it must consist of negative particles. So these are going to be our electrons. The ray is the same for any cathode. It doesn't matter what cathode we use. So it tells us that these particles are going to be found in all matter. And this is just a smaller version of the same experiment. So something else that J.J. Thomson discovered is the specific mass to charge ratio of the electron. So a little bit later, Robert Millikan came along and used that information. So again, Thomson found the mass to charge ratio of the electron, but didn't find the actual mass of the electron or charge of the electron. So he performed an oil drop experiment and was able to discover the charge of a single electron. And then plugging it into this equation, well, if you already know the charge and you already know the mass to charge ratio, then you can also figure out the mass of the electron. So let's see how this experiment worked.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
So again, going back to our equation, now that we know how the experiment works, Millikan took the mass to charge ratio that was discovered by Thomson, and then the charge that he discovered, and plugged those in to solve for the mass of the electron. And here's the value we have. So to understand the next step in atomic theory, or the next big discovery, we need to know a little bit about radioactive elements. So radioactive elements are going to be atoms that are unstable, so they're high in energy, and they spontaneously emit energy in different forms, different types of particles. So here they are, alpha, beta, and gamma, so going from those that are lower in energy to particles that are emitted that are higher in energy. So an alpha particle is going to be essentially a helium nucleus that's emitted from the atom, and it's not so high in energy, so just a piece of paper can block alpha particles. A beta particle is going to be a fast-moving electron. A piece of aluminum is strong enough to block a beta particle. And then we have a gamma particle, which is going to be a lot of essentially electromagnetic radiation being given off. And it is really, really strong. So to the extent where it can ionize other atoms, so basically knock out an electron. So this is the reason why gamma particles can actually do things like alter your DNA, because it's that strong. So again, we wanted to know just a kind of a foundation for what a radioactive element is, so we can talk about the next key discovery in atomic theory, and that will be by Rutherford. So at this point, the picture of what the atom looked like, according to J.J. Thomson, is that we have basically we have electrons, we have protons that are positively charged, and they're basically evenly distributed throughout. So Rutherford came along and performed this experiment because he had a different theory to test this out. And what he did was he took alpha particles that we just learned about, so a beam of alpha particles, and shot it at this piece of gold foil. And what he expected is that, well, if these plus and minus charges in the atom are evenly dispersed throughout, the alpha particles should just go right through. And what he saw is that, well, for the most part, they did go right through, but there were also some that were deflected. Okay, so this kind of pushed along a new theory, right? If everything was evenly dispersed throughout, the plus and minus charges, everything should have gone straight through, and this is not what he saw. So what came about now is that an atom has a nucleus. So that positive charge has to be concentrated in one general area. So that became the nucleus. So now this is what the atom looks like, our model of the atom. We have the nucleus where most of our mass is concentrated, and we have our protons and neutrons there, so our positively charged protons, and then we have our electrons that are in a cloud kind of around. And we'll talk more about the specifics when we get to orbitals later on. So here we have the mass of the electron, proton, and neutron. And also we have a comparison of the relative mass, just showing that most of the mass is concentrated in the nucleus. So if we move on to the next slide, I just want to remind you of calculating subatomic particles. So now we have electrons, protons, and neutrons, and we want to feel comfortable with using our best friend the periodic table to calculate each of those, or the number of each of those subatomic particles. So we have the symbol, we have the mass number, and we have the atomic number. So remember that our number of protons is going to be exactly the same as the atomic number. The atomic number, or the number of protons, is going to define what the element is. We have the mass number, that will be the sum of our protons and neutrons. So if we want to calculate the number of neutrons, we take our mass number, and remember we have to round it to a whole number, and we want to subtract the number of protons. All right, assuming that our atom is neutral, the number of protons, or atomic number, will also be the number of electrons. But remember, as soon as we get into charged particles, we need to make that adjustment. Either add the number of electrons if we're negatively charged, or subtract the number of electrons if we are positively charged. So what we want to know is how to determine the number of each subatomic particle using the periodic table. So the next thing is where the mass number comes from. So if we look at the different elements, well, we can look at, for example, hydrogen. It has 3 isotopes. So isotopes are going to be where we have the same number of protons, but the number of neutrons are different, or the mass number is different. And that mass that we see on the periodic table is going to be an average mass. So we'll talk about that more in a moment. But remember that we have the same number of protons, but the number of neutrons is different, which also means the mass number is different. Okay, so the mass that we see on the periodic table is going to be an average mass. So it's going to be a weighted average mass. If we think about different elements such as carbon, carbon has 2 isotopes. We have carbon-12 that will make up 99% of all of the carbon we have, but that 1% is carbon-13, so it's actually going to be a weighted mass. So what we can do is to calculate the mass that we get on the periodic table, we can take the fraction of that isotope, so it's going to be a decimal, okay, based on what percentage of all of the element combined is that particular isotope, and then the mass of that isotope, and we can do that for every single isotope. We can take the percentage of it in decimal form, multiply it by the mass of that isotope, and then add all of those up, and that's how we get the average atomic mass, or the weighted atomic mass that we see on the periodic table. So here's a sample problem, and you already have the answer here, but what I recommend doing is pausing the video and trying to work through this problem. So in this problem, you have 2 naturally occurring isotopes of silver. And what you want to do for this problem is we want to figure out the atomic mass. So how do we get that mass from the periodic table? And this is in atomic mass units. So what we need to do is we need to take the abundance. It tells you what percentage is that particular isotope. We want to convert it to a decimal. You can multiply it by the mass of that isotope. Do the same for the second isotope, and then add those up, and that's how you should get to this answer. All right, So here's a different type of problem. Again, I would pause the video and work through this one. So chlorine has two naturally occurring isotopes, and you have the mass of each of those isotopes. And it says if chlorine has an atomic mass given here, what is the percent abundance of each isotope? So in this case, something we can't do is we're not given the information about the abundance of one isotope, so we can't just subtract and figure out the abundance of the other isotope. Something we can do though is if we assume that X is the percentage of chlorine-35 atoms, we know that there are only two isotopes, so we can say 100 minus X is the percentage of chlorine-37 atoms. So we can set it up like an algebra problem. Okay, again, it's going to be a weighted average. So for each isotope, we're going to take the mass number times the abundance. In this case, our abundance is going to be represented by X. So we have X for chlorine-35, and then we said that 1 minus X, so we're now taking the 100% and setting it up like a decimal, so 1 minus X times that mass number, and we're going to set that equal to the mass that we get straight from the periodic table. And then it just becomes we have to solve for X, right? So once you go through the algebra, you get that X is going to be equal to 0.757737. So you get this value. And the way we'd figure out if we didn't know, the higher percentage is going to be that of chlorine-35. And we would know this because the mass that comes straight from the periodic table is a lot closer to 35. So it's 35.4527. So that tells us that that particular isotope is weighted more in the average. And then the smaller percentage is going to belong to chlorine-37.